In a previous discussion, we looked at how molecular orbitals were a quantum mechanical description for bonding, forming both bonding and antibonding molecular orbitals, the corresponding energy level diagrams, and how these could describe the bonding in homonuclear diatomic molecules. By describe the bonding, we considered things such as a bond order, bond length, and a new property, which were paramagnetism and diamagnetism. Let's extend this now to consider heteronuclear and also polyatomic. So when we began our discussion of molecular orbital theory, we tried to make sense of strange descriptions like this, strange representations, that got even stranger when we looked at um, not just s orbitals, but p orbitals that could form various molecular orbitals. And then that strange description here, which we're going to talk about today, which is how we would account for aspects of resonance. So this slide here contains a lot of information for the basics for what we were up to, how we were combining wave functions and taking linear combinations of atomic orbitals that could result in a bonding or an anti-bonding arrangement, the corresponding energy levels for those, and what was taking place then when we described something as bonding or anti-bonding. What did it mean to have attractions for an electron between both nuclei, and then also accounting for a decrease in the kinetic energy when the electron was now found in a larger volume? Or what does it mean to bring together the atomic orbitals and due to a node and forbidding electron density to be found in that bonding region, why did that lead to a raising of the potential energy? From there, we extended that after 1s, combined with 1s, 2s with 2s, to see what does it mean now when we combine p orbitals and form both pi and sigma, depending on the orientation. The resulting cases where we had electron density along the internuclear axes, making it sigma, or sigma star was along the internuclear axes, but we also had nodes present. Or in our degenerate pi orbitals that were either in a bonding or an anti-bonding arrangement. We had this idea then, if we have those particular molecular orbitals and we know the corresponding energy levels, let's fill them up. Let's fill them up because that will allow us to predict the corresponding properties. We had a slightly different ordering whether we were looking at our elements on the left-hand side of the periodic table versus the right. So questions up to here, pause for a second. This is bringing together a lot of the basics for molecular orbital theory. See if you can make sense of those ideas. When we extended that, we looked at two different diatomics that we're familiar with. And by familiar with, we've looked at their bonding before, be it with Lewis structures or valence bond theory, N2 and O2. I'd say in the case for N2, it was a picture that was quite similar to what we would have gathered from previous models. With the Lewis structure, I would say that N2 has a triple bond in it. With valence bond theory, we then characterize that as seeing a sigma bond and two pi bonds. With O2, however, I think we have a different description. With O2, notice how we were populating sigma, pi, and then anti-bonding, pi star. This was leading to Atkins' description that the double bond in this molecule is actually a sigma bond plus two half pi bonds, because we have contributions in both the bonding and the anti-bonding. That's a really different picture. We haven't had that description in any of our previous models. And we might ask, well, is that strange description correct? Well, we added to it that this would be explaining then the paramagnetism in O2. So is it correct? It sure seems like it's correct. This description of having a sigma bond plus two half pi bonds, something like that is necessary to be able to explain the paramagnetism that we have in that O2 molecule. We extended that then of populating our energy level diagrams for these other diatomics. We extended that a little bit by also then asking, well, tell me about if we have ions, if we are adding or removing electrons, and then making predictions for things such as the magnetic properties, connecting it to aspects of bond length, bond dissociation energy. So we want to be able to fill up diagrams like this and be able to interpret them. We are finishing our discussion by looking at a case like this, where we had a diatomic, but they were different nuclei. and the idea that the helium, more protons, brought the energy levels lower in potential energy. So that was leading to this offset. The idea of having an offset there in energy levels, that takes us to the concept of looking at heteronuclear diatomic molecules, because they will not be the same elements. We're not looking at F2, H2, N2, O2. We're looking at ones where the wave functions have different energies because they're coming from different atoms. How do we begin to account for that? So we're going to once again say that we're going to have a wave function for the molecular orbital that is a linear combination of the atomic orbitals, but we're going to have coefficients that are going to be accounting for the relative contribution of a given wave function. So let's connect this to other aspects of what we sought to explain with bonding. In one extreme case, we had a perfectly nonpolar covalent bond. If that's the case, then these coefficients would be the same. Our other extreme case was an ionic bond. With an ionic bond, we would have one of the coefficients very close to zero because it's capturing very little of the electron density. Where's the electron density? It's found on the anion. That's being introduced within this by having very different coefficients. And if we're somewhere in between, that's what a polar covalent bond would be. That's how we began to account for differences in electronegativity. Atkins makes the point here that these are referring to bonding orbitals. If we're talking about electrons in anti-bonding orbitals, then we're going to look at the contribution a little bit differently. Let's see what that looks like within an image. So here's one where it's showing the molecular orbital schemes calculated for a diatomic oxide. Maybe it's carbon monoxide, nitrogen monoxide. So notice it says they're calculated. The particular ordering for these, that's not something that we would necessarily know in advance. It's not something where you'd say, aha, I know exactly how those are going to be distributed. This is something that ends up being calculated. But could I make sense of this? Well, if I'm comparing things on the left-hand side, where on the left it was either carbon or nitrogen, and on the right oxygen, I would be saying, okay, oxygen, more electronegative, more protons, I would shift those lower in energy. Okay, I can make sense of that. Goes on to say that the sigma orbitals that we have here are formed from mixtures of s and pz orbitals, and that they're labeled simply here, 1 sigma, 2 sigma, etc. What do you think is going on with there? That's different than what we were looking at before. If we look more closely within here, let me go back. If we look more closely within here, consider this 3 sigma. It is showing that it has a line over here to the oxygen, contribution from the 2p, contribution from the 2s. When we're looking with our homonuclear, our case was pretty easy. We would say, okay, the energy levels are the same. Let's consider the spatial orientation. Let's consider how those now combine. We looked at one complication when we saw, okay, that's not strictly true. If we have some degree of a mixing of energy levels, it's not simply the case that we can look at them independently. That was leading us to have a somewhat different ordering on the left-hand side of the periodic table versus the right when we were looking at pi and sigma bonding molecular orbitals coming from the 2p. Same kind of thing here. We're going to say, okay, we're going to have, in some degree, a combining. I'm not talking about hybridization. I'm still retaining the atomic orbitals, but I'm asking, when they interact with other atomic orbitals, can I look at them strictly independently, or is there an aspect of combining? And in this case, we're saying, okay, there's an aspect of combining. So this sigma, this 3 sigma, is a sigma orbital that's predominantly coming from the oxygen 2p, but I don't want to ignore the contribution from the oxygen 2s. Its closeness in energy to the 2p is telling me that the oxygen 2p has a greater contribution, but somewhat contribution from the 2s. That's what it means when we see a particular molecular orbital with lines going to more than one atomic orbital. If we were to take those resulting energy levels and populate them, our task there is the same as what we've done before. We could consider the number of valence electrons for something like an NO cation, populate those, determine aspects of the bond order, consider the magnetism, and we could extend it a little bit here and ask, well, will the electrons have greater probability of being at the nitrogen or at the oxygen? So first task there, it's let's fill them up. I count that I have 10 valence electrons, and if I populate them, I have sigma sigma star, and then I've got pi pi sigma. Okay, my bond order ends up being 3. Triple bond. I see that they're all paired up, so I'd call it diamagnetic. This idea of will the electrons have greater probability being on the nitrogen or the oxygen? Recall that the oxygen, those are the atomic orbitals shown here on the right-hand side. So I'm going to look to see where the electrons are found in the molecular orbitals, and I'll see that they overlap more closely in energy with the oxygen. So that's what it means to say they have greater probability of being at the oxygen atom. It's not always the case. If I had even more electrons, then I began to fill up these antibonding. In those cases, those would resemble more the atomic orbitals on the left side. What does this now mean when we extend this for polyatomics? Same plan, we're again going to have molecular orbitals that are a property or are a description for the entire molecule. We'll get information about the energetics. Maybe it's a measurement. Maybe it's a computational approach. We'll populate those, and we'll use that to seek to gain an understanding of what's going on. So let's return to something that we looked at with valence bond theory when we looked at the bonding in benzene. We said that we had resonance structures and delocalized electrons. So I'm going to begin this by looking at where valence bond theory took me. So we looked at the structure, and we saw that we had sp2 hybridized carbons throughout. All in the same plane. For each carbon, I see 3 electron domains. Each of those then left an unhybridized p orbital that was perpendicular to that plane. So in our valence bond approach, we said, okay, this is what's leading to delocalized electrons. We have an overall pi bond that exists above and below the plane that we're now going to populate, and that arose from our unhybridized p orbitals. In a way, this was getting us close to the idea of a molecular orbital approach, because we were saying that that bond there now is a property of that entire region of the molecule. Where does molecular orbital theory take us? So instead of saying we have a single description for there, let's consider the corresponding energy levels that we would have. So here's an MO energy level diagram for this pi bonding in benzene. We have different ways that we can think of arranging the electron density. And when I say different ways of that, with molecular orbital theory, let's step back and say we had those p orbitals, unhybridized p electron on each of the carbon atoms. Let's consider aspects of the phase for those orbitals now. If I look at the bottom case here, lowest in energy, they could all overlap. All positive at the top, all negative at the bottom. No nodes whatsoever. Somewhat higher in energy, I would have a case where, notice on the left-hand side, all positive on the top. On the right-hand side, all negative on the top. I would put a node that would go between those two then. That's higher in energy. That's what we're seeing populated over here with the molecular orbitals. Lowest in energy, 2 examples where there's a node, degenerate with each other. 2 examples where there's 2 nodes, and 1 example where the phases are flip-flopping throughout, and you've got 3 different ways to bisect it. This is what is then populated within molecular orbital theory. We see we've got a total of 2, 4, 6 electrons, all in these descriptions for these bonding molecular orbitals. And in this case, I think we sort of have a degree from most bonding to most anti-bonding, and then aspects that are in between. What you see with the notation here, the HOMO and the LUMO, HOMO stands for highest occupied molecular orbitals. LUMO, lowest unoccupied molecular orbitals. That's notation that you're going to see again, I'm sure. A lot of times when we then talk about electronic transitions, photon comes in, we promote electron from the HOMO to the LUMO. So this is our description of how we began with a valence bond approach, but then we looked more closely at where the electrons could be found energetically when we were populating what could be considered a molecular orbital. Another idea that Atkins has is when it's looking at the molecular orbital theory to explain the bonding in SF6. So this is one that he tentatively brought up when he was introducing valence bond theory. Noting that, okay, if I use sp3, that could get me to a tetrahedral, but with 4 electron domains, but in SF6, that's an octahedral, so I'm going to add in d orbitals and consider them as part of the hybridization scheme as well. Now, if you recall at that time, I was a little tentative to do that. I said that I liked using valence bond theory up to a tetrahedral, but I wasn't really that comfortable to say, let's also use this now to extend for something like an octahedral. This is what I was thinking about. So even though you have d orbitals, it doesn't mean that energetically they're going to be useful to participate in the bonding. That's the point Atkins here is making initially. Goes on to say, okay, what would molecular orbital theory tell us is taking place? So he has a description here where he's not using d orbitals, but he ends up taking it and including some different features. So first of all, I read here that there's a fractional bond order. If I look at the image right here, I see aspects of bonding and anti-bonding, but added something new called non-bonding. What would be non-bonding? Well, I guess a lone pair is non-bonding, right? It's not contributing to either the bonding or the anti-bonding region. It's somewhere else. Within this one, I also see this notation of A and T and E. Within perusal, there were some good comments about this, trying to make sense of this. Because previously, we were just looking at examples that were sigma and pi. Now it looks like something else is going on. So I was liking the conversation. I like the conversation that I was seeing here of trying to make sense. What does this notation mean? What else could this be telling us? So let me look a little bit more deeply at this, just to fill in these details. So here's a closer look at what's going on. So within this, let me say, don't feel like this is a crucial part of the chapter. I just want to give you more details if you're interested for what's going on with this aspect, because it gives us some greater insight, I think, into molecular orbital theory. So first of all, within this one, the point's being made that the Lewis structure probably isn't that helpful. That the valence bond, if you say that I can make it work by including d orbitals, there's evidence that no, that doesn't really seem to be energetically available. It's not appropriate. So what would be appropriate if we're looking at molecular orbital theory? So with molecular orbital theory, let's first of all consider what are the atomic orbitals for that central atom in the octahedral, the sulfur. So let's start by saying, okay, it has a s orbital and 3 different p orbitals. Now we're not going to take these and hybridize them. We're just going to say those are the atomic orbitals for that central sulfur atom. How about then if we consider the fluorine atoms? So I'm going to have 6 of those, each of those at the different points on the octahedral. So I would be looking at the bonding coming from those in terms of their p orbitals. There's different ways that we can align those, and here's a few examples that are given. So within this picture right here, these 4, it's trying to show these are the 4 all within that same central plane, and this is what does it mean to be above and below. So it's showing different orientations for how you can take those p orbitals with different phases and have them pointed in different ways. What does it mean to say you have them pointed in different ways, in different shapes? So let's step back here. These 2 right here, this representation for the sulfur s orbital, or for this particular arrangement of the p orbitals, p atomic orbitals for the fluorine, they have that same subnotation here, this A1G. That's due to their symmetry. That's due to their resulting shape that they have. This idea of looking at the symmetry, that's what we're all about here. When we're looking at molecular orbitals, what were our 2 concerns? We were concerned about the energetics, and we were concerned about the shape, the symmetry, to see how these atomic orbitals could combine to form molecular orbitals. When we move on to polyatomics, we just have to look more deeply and have a way to better understand what is that symmetry. So therefore, how can molecular orbitals combine? Turns out that the symmetry or the analysis of the shape, that's a really big important part of chemistry. This table right here is telling me an analysis of the different ways that I can understand the symmetry in something that's octahedral. So that's what that symbol there at the top means. And when I say understand the symmetry, there's different ways you can manipulate an octahedron and have the shape return back to where it started from. So if I look at this example right here, what might I be able to do? symmetry-wise, what could I manipulate and have it return to where it started? Well, I guess I could flip it over top to bottom. That would be one way I could do it. I guess I could flip it over where this portion right here rotated over. That would also return back. Or where this one flipped over that way. Or I could turn it 90 degrees. Or I could invert it. I could take everything in one position, take it through the center to the opposite. Or I could have a reflection of a mirror plane. There's different things that I could do, different operations. That's what it's describing here at the top. These are different operations that are relevant when you have an octahedral. And both of these have the same description, meaning that when you perform an operation, it ends up looking exactly the same as where it started. That's what this notation is describing. These are similar in terms of their symmetry. If I consider this whole grouping with the symbol T, that's different. And let's just pick one example to see what does it mean to say it's different. Let's look at this example to see I, that means it's inverted. So if I were to take this p orbital, notice the phase is different. If I invert it and make the top go to the bottom and the bottom go to the top, it's flipped over. That's what it means to see this -1 value. It would look the same, but the phase value has shifted. Same thing within this example here for how the atomic orbitals are aligned. That's not true in this case where they're all pointed to the center, because if I flip it and I look at it, what it would mean at the opposite side, it still looks the same. That's just a real small sense of what does it mean to look at different symmetry options and the way that we have the different arrangements. So we're combining aspects then of the symmetry, the shape, with the energetics. The point's made that, well, why didn't we consider the fluorine 2s orbitals? We could consider their shape, but their energy is too low. They're effectively non-bonding. Instead, we need to consider the different arrangements for these 2p orbitals. Based on their symmetry, how do they combine with the atomic orbitals on the sulfur? That's what Atkins is talking about. These are the different arrangements. This is something that a computer program would calculate. These are a few of the different arrangements that are showing different bonding or non-bonding arrangements. The energetics, this is what Atkins is filling up. And he's pointing out that that's what these symbols now mean. This is based on the symmetry that you have. Here's an image that shows a little bit more fully where they're coming from, meaning what orbitals am I combining on the sulfur? Which ones am I combining on the fluorine? And it brings us then to this description where you could have some, let's just look at the fluorine here. You've got these deeper line 2s ones. The idea was that they were not contributing to the bonding. You have aspects here coming from the 2p, where you have different ones that will contribute to the bonding, and you have examples then that are non-bonding. This is what it means to use molecular orbital theory and to result in this fractional bond order, or as this author calls it, weird and eerie. Not going to overdwell on that, but I do think it's interesting. This is what it means to take a more complex polyatomic, because our simplest cases were just 2 nuclei, and see how does molecular orbital theory explain the bonding. I want to double back then to earlier ideas that we had about bonding. In a sort of review, I want to just mention what do I feel like were different skills that we worked on, and what would I expect that we'll be able to be asked to do on an exam. So when I double back to ionic bonding, we looked quite a bit at the energetics of that. We looked at examples and included ideas like ionization energy, electron affinity, and lattice energy. Being able to discuss the energetics leading to formation of bonding in something like NaCl, or explaining this figure, I think we have skills to do that. We did rankings in terms of lattice energy. I'd expect that we'd be able to both do a ranking and then explain it. Explain what's leading to those choices. Or another thing to explain would be our equation here describing the Coulombic potential energy. When we then extended that or shifted a little bit to get to Lewis structures, we began to consider covalent bonding when we had octets, and then moving beyond that. Skills within that, we were initially drawing Lewis structures and interpreting them to be identify, for example, radicals. When we did Lewis structures, sometimes they were neutral molecules, sometimes they were ions. We also evaluated aspects where we could have resonance taking place. Here was an example of one where the task was to evaluate and then consider what would be the most important Lewis structure. So I like this analysis where uh, different Lewis structures were being drawn. It's clear that different formal charges were being evaluated. What I would add to this, we'd want to be able to do that task, but then also explain our reasoning. Related questions might be, well, in your analysis, what are you using to identify the most important Lewis structure? My hunch is you're looking at aspects of the octet rule and formal charge. So what does that mean and how are you applying them? Or perhaps even most important Lewis structure. What does that even mean? When I read that, I'm thinking, okay, there's going to be different resonance structures. I'm going to be using criteria like formal charge, perhaps octets, and identifying the most probable resonance structure. That's what I think the most important Lewis structure is describing. When we look then at properties of bonds, we expanded our description a little bit by including aspects of electronegativity to expand or correct this covalent model, and polarizability for the ionic model. I think in both of those cases, Atkins connected the idea of resonance to both of these features, saying instead of saying you just have a single structure, you've got a combination of structures, whether it's a combination due to differences in electronegativity or manipulating the ionic model. He described resonance being present in both cases. You notice this question where he's asking for each pair, determine which compound has bonds with the greater ionic character. Well, what does the term greater ionic character mean? If you recall, he was placing covalency and ionic models on a continuum. So he didn't say this one's strictly ionic, this one's strictly polar covalent. It was being placed on a continuum. So this would be an example where I'd like you to be able to do the task, answer the question, but then also explain what the question is asking. The idea of being able to answer the question but explain what the question is asking. Here's another one in that same section where it's looking at polarizability. Arrange the cations in order of increasing polarizing power. Explain your reasoning. I think your explain your reasoning would be explaining what is polarizing power. What does that mean? So for example, what would this figure be describing? It says polarizing cations. Are all cations polarizing? Are some more or less polarizing than others? So in this section, we want to be able to answer the question, but have an understanding of what the question's actually asking us to do. Also within that section was connecting then bond strength and bond length and seeking to make predictions for those topics. So this would be an example where you're asked to do a ranking in order of bond length, and you're asked to explain your reasoning. What would I expect within this? I think you could do the task. What would be part, though, of the explanation? Well, it might start by considering differences in bond order, but then extend that and say, okay, that means that there's differences then in electron density that's found in the bonding region. It could even be connected to an image like this, where we looked at different potential energy wells corresponding to bonds of different strength, and we saw variations in terms of bond length. I think a really good question would be, can you do this particular ranking and then explain it and connect it back to this potential energy well? We also had provided data like average bond dissociation data. I think we also have data in that chapter about different bond lengths. Atkins here is describing these as being average values and adds a little bit, well, why aren't they strictly true? Or why aren't they always applicable? Just to give a quick example, consider something like this. These are the same molecules that were shown just a moment ago. Notice how, in this case, you don't have a single description for the carbon-sulfur bond. It's a fractional bond order. You have different contributions here. So if you were to look up and say the average value, you're not going to find a value that corresponds to carbon-sulfur in that table. You probably do the best job of trying to find something corresponding to carbon and hydrogen because they're single bonds in both cases. When we got to the VSEPR model, we were using that to do different things. do different things of being able to draw a structure beginning with the Lewis structure and then use VSEPR to consider things like the shape, bond angles. If you recall what we did, we began with the Lewis structure and identified both the electron and molecular domain geometry. We considered the ideal angles that we'd have present within that geometry, and then distortions to those due to things like lone pairs taking up more space than single bonds. Within this section, that's what I'd expect you to be able to do. Be able to draw the Lewis structure and then go through that entire process for the different atoms. When it comes to valence bond theory, we both did particular tasks, but then I think we want to be able to expand it and describe, well, why are we doing this? What is the theory seeking to accomplish? So what do I mean by that? For this question 17, it's taking a molecule and it's asking several things. Tell me the hybrid orbitals, bond angles, sigma and pi bonds, those kind of features. If we're going to extend that a little bit, how is valence bond theory explaining bonds? Well, it might be taking a molecule and including a sketch that shows how the bonds are being formed in the corresponding orbital diagrams. It could be this example here, use valence bond theory to describe the bonding in N2 and NH3. As applicable, talk about the role of hybrid orbitals or electron promotion. What is that? How is it part of valence bond theory? These are my attempt to say we will be using valence bond theory, but we also want to seek to connect it to how it works and what we can explain. And then finally, with molecular orbital theory, I think we have, once again, we use it and then we can also explain what we're doing. So in questions 18, 19, 20, I think we're using it to predict different properties. It might be aspects of bond strength, ionization energy, electron affinity. I'd add the property of magnetism to that. Looking at various diatomics, could be neutral, could be ions. To then extend it a little bit and think about, well, what else is going on? How are we using it besides filling in these diagrams? An example I list here on the left, compare and contrast the bonding in O2 using valence bond theory and molecular orbital theory. That, I think, is getting at the explanation part. Or, what do these equations represent in the context of molecular orbital theory? What is this representing as we think about taking linear combination of atomic orbitals? And what does it mean to be able to do it in different ways? So within this group right here, each of these I think are topics involving bonding. In each case, I think on our exam, expect an open response question and a couple choices within each one. We're going to move from here now into looking at different states of matter. Our next step is we're going to begin to look at gases. So what I'd recommend is for each of these within the bonding part, revisit the different questions that I have as I step through within here. Ask yourself, okay, what kind of answers do I have for these? Do I think I have a good description for what's going on, in particular when it comes for the explaining part? Because for several of these, I think we want to be able to answer the question, but we also want to explain the process and what